Okay, paper number 3 in our series on sprinting is a 2000 paper by Weyand et al. Titled Faster Top Running Speeds Are Achieved with Greater Ground Forces, Not More Rapid Leg Movements. Another example of the kind of title that I love in science, where the key finding and main take-home message is right there in the title. I'll probably sound like a kiss-ass on YouTube if Peter listens to this. He's got a YouTube channel as well. But this paper is, in my possibly biased opinion, the most important paper in sprinting biomechanics, and is one that, for me personally, was very influential on me. I read this paper for the first time in, I think, 2006 or 2007. I was a graduate student at the time, and I was doing part of my dissertation on maximum sprinting speed and muscular limitations to maximum sprinting speed. And I read this paper then for the first time when I was reviewing the literature on that topic. And it forwards an idea that is, I was going to say simple, it's not necessarily simple, but an elegant idea from basic physics and classical physics on how maximum horizontal speed is limited not by horizontal force and not by cycling your legs quickly, but by vertical force. So the rate at which you can generate vertical force against the ground is what limits your horizontal speed. Which again here they give a fairly elegant explanation for based on classical physics, but was new to me, was not a way that I'd ever thought about sprinting before. And so reading this paper really opened my eyes to that idea and really changed how I think about sprinting biomechanics and locomotion biomechanics in general. So this was a paper that for me that was very influential on how I think about biomechanics. So a few things that I wanted to highlight here in this paper. It's all about limits to maximum speed, and the central idea is that horizontal speed is achieved by generating vertical force primarily. Okay? So kind of two elements of speed here. Sprinting is, of course, all about speed, right? But what type of speed? Primarily, what limits you biomechanically from achieving a certain maximum horizontal speed will be the speed at which you can generate vertical force between your feet and the ground. It's not so much limited by the horizontal force that you can generate, and not so much limited by the speed at which you can cycle your legs. Okay? Now, remember here, though, there are kind of two different perspectives we can take on maximum speed and limits to maximum speed. We can talk about what limits an individual's maximum speed, like if I'm on a treadmill and I start at 5 miles per hour and I slowly tick it up to whatever my top speed is, I'll be doing different things biomechanically in my gait while I speed up. And what is it that I change? What changes about my biomechanics as I speed up over that range of speeds that I'm able to run at? And what is it that I get to at my max speed that I'm not able to change anymore? That would be an example of within subject speed. The other perspective here, and the one that the paper is more about, is a between subject comparison of speed, or between subjects comparison of speed, where everybody has a maximum speed that they can't exceed, but some people have pretty fast speeds there and some people have slower speeds. So what is it that makes some people's maximum speeds faster than others? And this paper argues that it's not the ability to cycle the legs faster, it's the ability to generate sufficient forces against the ground in the vertical direction faster, or in sufficient magnitudes in sufficient time. Okay, two key figures that I wanted to highlight in this paper. Figure 2 here is showing the within subjects data, or an example of within subjects data. And figure, I think, 5 later on is kind of the punchline, the take-home message of the between subjects data in terms of biomechanically, what is it that makes some people faster sprinters in terms of top speed than others. So let's start here in figure 1, figure 2. In each one of these panels, on the x-axis is the speed at which the particular individual shown here in these data, these are data on just one person, but most people show trends similar to this. They had one individual here running on a treadmill at a range of speeds, at many different speeds within the range of speeds that person is capable of running at. Starting on the far left here at about 3 meters per second, which is a moderate endurance type speed for most people, most healthy fit people, all the way up here onto the right, to this person's maximum sprinting speed, which looks like about 9.5 meters per second or so, which is a pretty fast sprinting speed. That's not a speed that most untrained people or most untalented people in terms of sprinting would be able to sustain. That's a very fast sprinting speed. In the top panel here is showing across that range of customary speeds. So as this person increased their speed from what was for them probably an easy jog up to their maximum sprint, biomechanically what changed as they were speeding up. In the top panel is showing their stride length at all those speeds in the black dots and their stride frequency at all of those speeds in the white dots. And reminder of how those things relate for speed and why they're important for speed. They directly are your speed, essentially, the combination of those two things. Speed is stride length, how far you go each stride, times stride frequency, how quickly you're taking your strides or how frequently you're taking those strides. Strides per unit time, essentially. You could also, since stride frequency is the inverse of stride time, right, strides per second, you can also think of speed as stride length divided by stride time. Okay? So as I increase my speed, I could do that by increasing just stride length, or I could just increase stride frequency, or I could increase them both. I could even increase one a certain amount and decrease the other one as long as it wasn't too much and still hypothetically increase speed. But to change my speed, I have to change one or the other of these two stride parameters here. And how do I do that when I'm trying to run at faster and faster speeds? What people tend to do is, as you're increasing over these first like 3 dots here, so from like a slow endurance running type speed to like a fast endurance running type speed. So over these first 3 to 4 dots here, you can see that they do that primarily by taking longer strides. And they don't really change their stride frequency all that much. So you take longer strides, cover more distance per stride, but cycle your legs at roughly the same rate. Okay? As we then go in these middle dots from like a fast endurance run to something beyond an endurance run, not an all-out sprint, but like an aggressive speed, a speed that I probably couldn't hold for more than a minute or two at most. There, I'm still noticeably increasing my stride length, but now I start increasing my stride frequency a little bit. Now I start cycling the legs faster. Okay. Then, as I go from a slow sprint in these last few dots, as I go from a slow sprint up to my maximum sprint, then something interesting happens, right? My stride length kind of levels off. I can't really increase it any further. And I keep increasing my stride frequency, and I increase it in these pretty big chunks towards the end here. Okay. So in going from slow to moderate running speeds, I do it mostly by stride length. And in going from moderate to maximum running speeds, I do it mostly by stride frequency. Okay. So when you look at these data, you might think, well, it looks like the title of this paper is false, right? Faster top running speeds are achieved not by more rapid leg movements. Well, that doesn't look like it's the case, right? It looks like to run at faster speeds, I gotta cycle my legs faster, right? There's a key word here in the title that invalidates all that I just said. Faster top running speeds. Okay? So this is talking not about an individual increasing their speed within the range of speeds they're able to do, like speeding up from a jog to a sprint. It's talking about comparing individuals, about comparing somebody with a fast max speed to somebody with a slower max speed. What is the faster person doing biomechanically that's different from the slower person and is allowing them to run at that faster speed? Okay. Another perspective you could take on that would be, this is my max speed here for this particular person, about 9.5 meters per second. What if I wanted to get over to this line to 10 meters per second? Biomechanically, what would I have to do? Would I have to somehow increase my stride frequency further? Would that be the way to speed up? Would I have to train to increase my stride length a little bit, or have it plateau at a longer length there? What should I do? What would allow this person to become faster, to reach a new faster top maximum speed? Another perspective you could take on that is if I put a dot on here of somebody who had a faster speed, what would their stride length look like? Are they taking longer strides? Are they taking faster stride frequencies? What's explaining the greater speed here? We could do that by looking at someone that's faster. We could also look at something that's faster. Like, for example, we could look at the fastest animal, at least the fastest terrestrial animal, the cheetah. I think I show cheetahs in every class I teach. I really like cheetahs. They're the coolest animal in the world, if you ask me. Cheetahs have a top sprinting speed of briefly sustaining speeds of around 70 miles per hour, which is more than twice as fast as the top speed the fastest human sprinters can reach. They go from 0 to 60 miles per hour in about 3 seconds, which is not as fast as every car on Earth, but far faster than most cars on Earth, certainly faster than any car I'll probably ever drive. So they're absolutely amazing biological machines when it comes to sprinting. And where does their speed come from? From this, stride length and stride frequency framework. Is the cheetah fast, 2 to 3 times faster than a human sprinter because they have incredible superhuman stride length or superhuman stride frequency or both of these things? What's explaining the cheetah's speed here? Well, we can kind of get a shot at that by comparing stride parameters for the cheetah to stride parameters of the human. So I'm just going to draw a line here, if I can, from my fastest stride frequency here at my top human sprinting speed all the way to the left there. And it looks like my fastest stride frequency at this person's top speed was about 2 strides per second. So they completed two full strides, 2 full gait cycles every second. Okay? So keep that number in mind, two strides per second. Then let's look at the cheetah and see what they're doing. Cheetah on the left, I'm pretty sure is filmed in real time here, so let's focus on that one. Cheetah on the right, I'm not sure is in real time for sure, but cheetah on the left, I know for sure is in real time. So you can see I don't know how fast they're going, but the background there is just blurring by. They're probably going, I don't know, twice, maybe 3 times as fast as a normal human sprinter. But can we reason out their stride frequency? We can't really measure it too well, but if you look at my clock up here, you can count seconds, 1001, 1002, 1003, and then count how many strides cheetahs do in stride, 1, 2, 3, 4, 1001, 1002, 1003. So it looks to me like cheetahs doing about 2 strides per second, right? Then we go back to the human. What did they do? 2 strides per second, right? So cheetah running at 60 miles per hour, 2 strides per second. Human running at 20 miles an hour, also 2 strides per second. So why is the cheetah fast, at least from the perspective of stride parameters? Is it because of superhuman stride frequency? No, stride frequency is normal compared to a human. It's because of superhuman stride length. So cheetahs are fast not because they cycle their legs at incredible rates. They're fast because they cover a tremendous amount of distance with every stride that they take. Okay, so stride length explains the cheetah's speed beyond a human, not stride frequency. Okay. Now, let's dig deeper here. Why is the cheetah able to have these incredible stride lengths? Well, it relates to the ability to generate forces under their little cheetah paws there. And we can learn something about human sprinting and human sprinting speed and why some people are faster than others from that perspective. And what is that perspective? Let's briefly look here at figure 1. This is showing in the top a person doing 3 steps, so a step with the right leg, a step with the left leg, another step with the right leg, and a full stride here again would be 2 consecutive steps, right? The step with the right leg and then the next step with the left leg as well. Okay? The right leg here, when it's in contact with the ground, would generate a vertical force, and the left leg would also generate a vertical force. Okay? I'm going to highlight here the force during the right step, right here. Okay. So this is the vertical force under the foot when this person is doing this step with the right leg. And this is the force that on average, so the average vertical force over this time here, this is the force that has to average out to being half the person's body weight. Okay? Assuming here that if I add in the left stride as well, or left step as well, and make this a full stride, a step with the left leg, a step with the right leg, on average, the vertical force over this time, over this about 600 milliseconds or so, including these periods of 0 here in the airborne phase, the average vertical force during that whole time has to be equal to this person's body weight. Okay? Why is that? Well, this is the vertical force. It's opposing gravity. The whole time across here on this stride, gravity is pulling their center of mass down with a force equal to their body weight. So to avoid having the center of mass sink on average, like every step, sinking into the ground here downward, the average vertical force they generate between their feet and the ground has to be equal and opposite to that gravitational force. Okay? So it's not saying the peak force is equal to body weight. It's not saying the average force while it's non-zero, while their foot on the ground is equal to body weight. It's saying the average force over this entire stride, so all data points on this black line averaged over this entire time has to equal body weight to avoid sinking into the ground. Okay? Now, what does that have to do with limiting maximum speed? Remember I said this is true for walking, it's true for running, it's true for sprinting, it's true for all forms of legged locomotion at all speeds. Average vertical force has to be body weight. What does that have to do with limiting speed? Well, notice here what was happening in figure 2 when this individual sped up. This panel here is showing the timing, the durations of certain parts of the stride cycle. In particular, these white dots are the duration of the ground contact phase, the amount of time their foot was in contact with the ground. Notice that it's decreasing as we speed up. Okay. Why is it decreasing? Well, it's largely because stride frequency was increasing, which means the total duration of the stride is decreasing. You're performing the strides more quickly, so there's less time for each stride, including less time with the foot in contact with the ground. Okay. So imagine here, as I speed up faster and faster, this length of time right here, the amount of time my foot's actually on the ground, both in terms of like sheer, like absolute time, like milliseconds, and in time in terms of like the fraction of the gait cycle, like percentage of the full stride cycle. Regardless of how you want to splice it out there, the amount of time you spend with your foot actually on the ground decreases as you increase your speed, as you run faster and faster. So there's less time at faster speeds with your foot in the ground, less time to generate this vertical force, and less time to generate forces that are big enough that when you average them over the full stride, including these airborne periods with no force, which are getting relatively longer and longer for the full in terms of fraction of the stride as you go faster and faster, less time available to generate bigger and bigger vertical forces such that the average force is equal to gravity and is still offsetting your body weight every stride. Okay. So that's really at the core of this paper's theory that they were testing with measurements on human subjects for what limits maximum speed. The time available for the foot to be on the ground and the ability of the individual to generate big enough vertical forces in that increasingly smaller time to offset gravity, to generate an average force that was big enough in this brief period of time to get an average force over the whole stride and over many strides that's equal to body weight. Okay? This is why you hear about power, and this isn't really power. This is this isn't work. Power would be work divided by time, not force divided by time. But this is largely why you hear about power and rate of force development being so important for quote unquote explosive tasks like this, like sprinting or high intensity tasks. You have very little time to generate very big forces to meet the basic constraints of physics here, such as offsetting gravity so gravity doesn't win out and sink you into the ground. Okay, if this theory is correct, if the issue here for running at fast speeds, if the explanation for why some people are faster than others is that they can generate sufficient forces more quickly, then we should see, as we compare faster people to slower people, we should see as they go faster, the faster people should actually be spending less time with their feet in contact with the ground than the slower people. And during that time, they should be generating greater average vertical forces, such that when we average over full strides, they're still offsetting gravity, which they have to avoid falling over. So is that what we saw? When we compare fast sprinters to slow sprinters, do the fast sprinters spend less time with the feet on the ground, and do they generate greater average forces during that time? They did indeed, and that's what's shown here in figure 5. On the x-axis of these two figures, and the key ones here are the top two, figure 5a and figure 5b, on the x-axis is the speed at which people sprinted at. So this is not like figure 2 where it's one person. Each one of these dots is an individual running at their personal maximum speed. Okay, so the slowest people here ran at about 6 meters per second, which is not slow. I don't want to disparage anybody's efforts here, but that's not a super impressive max speed. Compared to on the far right, a couple people running at looks like a little bit over 11 meters per second, which is very fast. That's a very impressive sprinting speed, especially for treadmill running, which they were studying here. So we can see a general trend here that if we look at faster people versus slower people, the faster people were generating larger average vertical forces when their foot was in contact with the ground, or a general upward trend in these vertical force averages. And they were spending less time on average with their foot in contact with the ground, a general downward trend in those data. So even though they had less time to generate forces, they were generating a greater average vertical force in that time. Okay? So if you divide these forces by these times, you would get a very large difference in the average rate of force development for the fast sprinters versus the slow sprinters. Okay?